So in today's lecture, we will see what is this epitaxy. Because in previous lectures we have seen what is the fabrication of nanomaterials or nanostructures. What are the fabrications? What are the different processes that were fabricated? And we have seen certain characterization techniques, and we have seen certain differences between different types of characterization techniques. And today's lecture, we'll see what is this epitaxy. Epitaxy is nothing but molecular beam epitaxy. This is also one of the fabrication method for the fabrication of nanomaterials. Right. So, if you come to the classification of electronic materials, compound semiconductors allows us to perform band gap engineering. Compound semiconductors allows us to perform band gap engineering by changing the energy band gap as a function of position. Right. So this allows the electrons to see the engineered potential. That guide electrons or holes in specific direction, or even trap them in a specific regions of devices designed by the electrical engineer. For example, consider the specified band diagram of gallium nitrogen or gallium indium and nitrogen or gallium nitrogen LED structure. Right? Electrons and holes can be localized or trapped in a very small region. Enhancing the chance of interacting or recombination. And this is one of the great achievement for the light emitters. So that is our light emitting diode. So light emitting diodes are nothing but the materials where the recombination of the charge carriers results in the release of some light energy. Right? So light energy. So we call them as LEDs, right? So if you come to the LEDs, light emitting diode. Light emitting diode is a diode, right? It's a diode where the recombination of charge carriers takes place. So that means the energy is being converted from electrical energy to light energy. Right. So that was what the classification of electronic materials was framed. Right. Compound semiconductors allows us to perform band gap engineering by changing the energy band gap as a function of position. So compound semiconductors allows us to perform band gap engineering by changing the energy band as a function of position. So this allows the electrons to use engineered potentials that guide electrons or holes in specific direction, or even trap them in specific regions of devices designed by the electrical engineer. Example: consider the simplified band diagram of gallium nitrogen or gallium indium nitrogen, or GaN, so gallium LED structure. So electrons and holes can be localized. That means they can be trapped in a very small region. So that the enhancing will interact with the recombination. So this is what the general explanation what we can give for light emitters. We have the electron conduction, electrons valence band. Valence band is maintained at the lowest energy, and conduction band is maintained at higher energy. So the light interacting enhances the recombination, which is a great achievement, for light emitters. Right? It is a great achievement for light emitters. Okay. Now, if you see the classification, for some more classification, right? So if you see the same factor that compound semiconductors allows us to perform band gap engineering by changing the energy band gap as a function of position, as we have seen. This allows electron to see the engineered potentials. This allows us electron to see the engineered potentials that guides electrons or holes in specific directions, or even trap them in a specific regions of devices designed by the electrical engineer. Right? Consider the band diagram of gallium arsenide MOSFET, right? That is metal oxide field effect transistor. Electrons in the transistor channel can be confined in a very thin, that is 50 to 100 angstroms. Okay. Sheet known as a two-dimensional electron gas, that is 2DEG, we call it as two-dimensional electron gas. This thin layer is very quickly depleted. Or easily depleted, emptied of electrons by application of gate voltage. That is what the repelling electrons makes such transistors very fast. So this technology enables high-speed communications, modern radar, radio detection and ranging, and similar applications. Right. So here, if you see the band diagram of gallium arsenide MOSFET, so electrons in the transistor channel can be confined in a very thin, around 50 to 100 angstroms sheet known as a two-dimensional electron gas. So this thin layer is very quickly, easily doped, emptied by electrons by application of gate voltage, that is what repelling electrons, making such transistors very fast. This technology enables high-speed communications, modern radar and similar applications. Right. So this is what the fundamental fact what we need to understand regarding the MOSFET, where we have the aluminum gallium arsenide and we have gallium arsenide, and this is what the 2DE channel, 2D, two-dimensional electron gas channel. So this thin layer is very quickly or easily depleted, emptied of electrons by application of gate voltage, or repelling electrons. Making such transistors very fast. This technology enables high-speed communications, modern radar and similar applications. Right. So how do we produce these energy engineered structures and devices? So that is what epitaxial semiconductor and dielectric deposition techniques. So epitaxial is derived from the Greek word for skin. More specifically, thin skin. So epitaxial resembles more thin skin. So this was being derived from the Greek word. So epitaxial is derived from the Greek word for skin, more specifically thin skin. So thin layers of material are deposited on substrate. Right? So temperature and substrate determines the physical structure of the deposited films. Temperature and substrate determines the physical structure of the deposited films. So temperature and substrate determines the physical structure of the deposited films. Right? And other is low temperatures or non-crystalline substrates. Materials end up with amorphous or polycrystalline materials, high temperature and crystalline substrate, and these need to have an existing crystalline wafer so as to see the crystallization process. Films that retain the substrate basic crystal structures are epitaxial. Right? Films that retain substrates with substrate basic crystal structure are epitaxial. Right? So this is what the fundamental factor what we need to understand. Epitaxial is derived from the Greek word for skin, more specifically thin skin. Thin layers of materials are deposited on a substrate. Temperature and substrate determine the physical structure of the deposited films. Low temperatures or non-crystalline substrate materials end up with amorphous or polycrystalline materials. High temperature and crystalline substrate and need to have an existing crystalline wafer so as to see the crystallization process. So films that retain substrate, basic crystals are called epitaxial. So epitaxial in the sense it's a Greek word. It's a Greek word that has been more specifically called thin skin. So epitaxy, there was a single crystal semiconductor, that is what epitaxy. We can grow the crystalline semiconductors by raising the temperature to allow more surface migration and by using a crystalline substrate like silicon, gallium arsenide, indium phosphorus wafers, etc. So single crystal materials mimicking the crystal structure of the layer is given below. So these are the Adam atoms lower level. So this is a king side, so terrace edge, and this is the terrace level. So this is the terrace level, right? Terrace edge, king side, and this Adam atom is lower level. So this is what the macroscopic view of semiconductor surface during molecular beam epitaxy growth or evaporation. So here, so we can grow in the sense, instead of the word deposit, we use grow, because growing to describe the tendency, it describes the tendency of the deposited material to mimic the crystal structure of the crystalline substrate material, right? So that's why we are using the word called grow instead of depositing. So depositing a thin layer, depositing a thin layer on either silicon wafer or gallium arsenide, indium phosphorus wafer. So we can frame the single crystal material mimicking the crystal structures of the layers below. Right? So this is how we can frame. That is what the microscopic view of semiconductor surface during molecular beam epitaxy, growth or evaporation. So this is what the crystalline order. Right? So this is what the crystalline order. Water molecules or the H2O forming snowflakes, and atoms forming a semiconductor. So this is what taken from slides were taken from some of the slides were taken from Georgia Tech. So need 2 volunteers to demo on how crystal forms naturally due to repulsive electronic bands. So if you see the epitaxy, importance of lattice mismatch. The lattice constant of the epitaxial grown layer needs to be close to the lattice constant of the substrate wafer. So the lattice constant of the epitaxial grown layer need to be close to the lattice constant of the substrate wafer. Otherwise, the bonds cannot stretch far enough and dislocation will result. This lattice constant of the epitaxial grown layer needs to be close to the lattice constant of the substrate wafer. Otherwise, the bonds cannot stretch far enough and dislocation will result. So this is what the commensurate. So this is what the structure. This is what the epitaxy, and this is what the substrate. Right. So this is what the dislocation. Dislocation in the sense, dislocation may exist due to the strain in the material, the strain or stress in the material. So this is what the dislocation where we can observe strained but unbroken bond. This is strained but unbroken bond. This part. Okay, this is where the dislocation is increased. So this is what commensurate, and strain released incommensurate. Right. So this is pseudomorphic. Strain elongated but unbroken bond. Strain is elongated but unbroken bond. So that is strained, compressed but unbroken bond. So that is what here it is elongated where it is compressed. So the lattice constant for the epitaxial grown layer needs to be close to the lattice constant of the substrate wafer. That means they should be interact. There should be a mismatch. There should be a synchronization between the lattice constant of the material and the lattice constant of the substrate wafer. Otherwise, the bonds cannot stretch far enough, and there will be voids in the crystal parameters. There will be voids in the crystal parameters. Voids in the sense that we can find there are certain dislocations. So these dislocations, one is due to commensurate, so strain, relaxed, incommensurate, and pseudomorphic. So epitaxial growth process can be divided into commensurate, strain relaxed, incommensurate, and other is incommensurate but pseudomorphic, right? So these are the different types of epitaxial growth process included into that particular epitaxial growth process, right? So epitaxial growth process can be divided into commensurate, stress level, strain level, and incommensurate. So what is the importance of this lattice mismatch? The lattice constant of the epitaxial grown layer needs to be close to the lattice constant of the substrate wafer, right? The lattice constant of the epitaxial grown layer need to be close to the lattice constant of the substrate wafer. Otherwise, the bonds cannot stretch far enough and dislocation will result, right? So this is what the MS with dislocation, right? So this is what the dislocation takes place due to the mismatch between the lattice constant of the wafer and the lattice constant of the material. Lattice constant of the epitaxial grown layer needs to be close to the lattice constant of the substrate. Otherwise, the bonds cannot stretch far enough and dislocation will result. So this is what the aluminum, and this is on the silicon, right? So this is aluminum is being deposited on the silicon. So this is what the TEM image, a TEM comparable to the schematic. This shows that 1-1 planes of aluminum epitaxial overgrown on silicon and the 1-1 plane of the silicon substrate. So that means the lattice constant, there will be a mismatch between the lattice constant and the epitaxial film that is grown on the material. So as a result, some voids or some dislocations may exist. So in case of silicon epitaxy, used for high purity layer growth, that is alternative augmenting a duned zone, can form very thick and doped structures around 30 to 100 micrometers, not possible with implantation or diffusion. Such thick pure layers are often used in power devices with thinner 1 to 5 micrometer are commonly used for many CMOS technologies and bipolar technology. We want the reaction to occur at the gas or vapor boundaries. However, the high temperatures, that is silane around 650 degrees to 800 degrees, used for enabled surface migration also result in gas phase. A decomposition of silane resulting in particles and this is very bad as particles tend to fall on the wafers. Higher quality materials occurs at high temperatures than 800 degrees centigrade. Instead of silane, we can use chlorosilicines that are more stable up to higher temperatures are more commonly used. Dichlorosilane, that is SiH2Cl2, is the most common and allows growth around a growth at approximately 800 degrees to 1050 degrees centigrade. Higher temperature is possible. So if you see, so this is what the temperature variation versus this. So we can see this is what the Arrhenius field, Arrhenius field, where we can see the Arrhenius. This is where we can see the behavior of this particular material shown, right, for different temperatures and different. So in case of metal oxide CVDs, we have this particular metal organic chemical vapor depositions primarily used for 2 to 6 and 3 to 5 semiconductors, especially metallic oxides and metals. Used for high purity layer growth, can form very thick doped structures 30 to 100 micrometer, not possible with implantation or diffusion. Such thick pure layers are often used in power devices with thinner 1 to 5 micrometer are commonly used for CMOS and bipolar technology. We want the reaction to occur at the gas or vapor boundary. However, high temperature silane around 650 to 800 degrees centigrade used for enhanced surface migration also result in gas phase decomposition of silane, resulting in particles. This is very bad as particles tend to fall onto the wafers. Higher quality fever defects material occurs at higher temperatures than 800 degrees centigrade. Instead of silane, chlorosines that are more stable up to higher temperatures are more commonly used. So dichlorosilicon, that is SiH2Cl2, is the most common and allows growth at 800 degrees centigrade to 1050 degrees centigrade, which is possible. And this is the harmonious behavior of variety of silicon containing growth species after, right? So this is what the silicon epitaxy is. So if you go for MOCVD, so we have metal organic chemical vapor deposition. Many materials that we wish to deposit have very low vapor pressures and thus are difficult to transport via gases. One solution is to chemically attach the metals, that is gallium, aluminum, copper, to an organic compound that has very high vapor pressure. Organic compounds often have high vapor pressure. For example, alcohol has a strong odor. So the organic metal bond is very weak and can be broken via thermal means of vapor, depositing the metal with the high vapor pressure, organic being pumped away. Care must be taken to ensure little of the organic byproducts are incorporated. Carbon contamination and unintentional hydrogen incorporation are sometimes a problem. This is what we can see about for primarily used for 2 to 6 and 3 to 5 semiconductor specific metallic oxides and materials. So this is what we can see metal oxide chemical vapor deposition, where we can deposit. This is one of the instrument that we can see. So we have optical probes, we have show head water cooling systems, we have double O-ring seals, so suspectors, water cooled chambers, we have quartz liner, and we have top plenum chamber, gas inlet bottom plenum chamber, 3 ozone heater, thermoscouples, right? So these are what we can see. The commercial Thomas Swan metal oxide, metal organic chemical vapor deposition. So in case of molecular beam epitaxy, it dominates 3 to 5 electron market and strong competitor in upper and laser market, and offers the highest purity material due to ultra high vacuum condition and the best layer control. Almost any fraction of atomic layer can be deposited and layers can be sequenced, and one layer at a time. For example, gallium, then arsenate, and then gallium excipher. So like that, there will be alternative deposition method, right? So in an ultra high vacuum chamber, ultra high purity materials are evaporated. Because of this very low pressure, the mean free path is very long and can be hundreds of meters. Thus, the evaporated materials travels in a straight line at the molecular beam towards a hot substrate, resulting in highly efficient raw materials usage. Once on the substrate, the atom or molecule moves around until it finds an atomic site to chemically bond to it. Shutters can be used to turn the beam flux on and off, and the flux of atoms or molecules is controlled by the temperature of the efficient cell. Right. So this the molecular beam epitaxy develops the 3 to 5 electronic market and strongly competitive upper and laser market, offers the highest purity material due to ultraviolet conditions and the best layer control. Almost Any fraction of an atomic layer can be deposited, and layers can be sequenced one layer at a time. For example, gallium one time, and then the arsenic, and then gallium, like that. Right. So we can deposit several layers. Right. So in a ultra high vacuum chamber, ultra high purity materials are evaporated. Because of the very low pressure, the mean free path is very long, can be hundreds of meters. Thus, the evaporated material travels in a straight line towards a hot substrate, resulting in highly efficient raw materials usage. Once on the substrate, the atoms or molecules move around until it finds an atomic site to chemically bond to. Shutters can be used to turn the flux beam on and off. The flux of atoms or molecules is controlled by the temperature of the efficient cell, that is evaporation source. So this is what the molecular beam epitaxy, which will be done in a clean rooms, and this is what the instrument what we have. And we have the reed gun, and we have, this is what the molecular beam epitaxy, we have indium gallium material, right? So this is what the material, it is what the somewhat figure what we have framed. So this resembles the indium and gallium material, so which are to be deposited on the substrate. So this is what the molecular beam epitaxy layers that is grown, where we can find the dislocations. So how do we create band gap engineered structures? Repeating a crystalline structure by atom addition, chemistry controls epitaxy to ensure that, for example, gallium bonds only to nitrogen and not GHE or NN bonds. So this is what we can frame the epitaxy layers, right? So this is what the energy engineered behavior in compound semiconductors. We have the valence band, we have the conduction band. So the potential contribution we will use in this class are all possible or common in device structures. Some may represent grown in potentials or naturally occurring potentials. Lattice vibrations, for example, lattice vibrations or thermal vibrations, including periodic potentials such as lattice ions. So this is what plasma enhanced chemical vapor deposition techniques, right? So these are some of the deposition techniques where we need to understand how to fabricate the thin films, right?
Like, share and subscribe. Hit the bell icon for more updates.